full professor at the University of Freiburg, where he directs the Robot Learning Lab. He is affiliated with the Department of Computer Science, the BrainLinks Brain Tool Center, and a founding faculty of the LA's Unit Freiburg. He received his PhD from the University of Freiburg and his master in robotics from Carnegie Mellon University. Abhinav's research lies at the intersection of robotics, machine learning, and computer vision, addressing fundamental problems in perception, state estimation, and decision-making to enable robots to operate reliably in complex and diverse open-world settings. For his research, he has received multiple awards, including those from IEEE IROS and some NVIDIA Research Award as well. Abhinav is a DFG Emmy Noether AI Fellow, a scholar of the LA Society, IEEE senior member, and co-chair of the IEEE RAS Technical Committee on Robot Learning. He is a senior editor in IEEE Robotics and Automation Letters, as well as an associate editor and area chair for multiple conferences and journals. Many aspects of his research have been prominently featured in wider media such as the Discovery Channel, NBC News, Business Times, and the Economic Times. We're very thrilled to have you today, Abhinav. Thanks a lot for accepting the invite. The floor is yours. Take it away.
Hey, thanks a lot for the introduction. Thanks for having me. It's great to be here. So today I'll share some of our relatively new work. So it's the first time I'm talking about this. I spoke a little bit about this at Coral at a workshop, but yeah, so I'll talk about a recent work towards long horizon mobile manipulation in everyday environments, and also share some thoughts about the key challenges that we need to address in perception, articulation, reasoning, and policy learning to complete essentially really long horizon tasks that span extensive spaces and where the robots need to do a diverse set of actions. So let's start that we all know that robots have revolutionized manufacturing. Today, all of our cars are made by robots. Probably anything that you order online in e-commerce at some point has been handled by a robot before it gets to your actual hands. But if we look at the environments that these robots operate in, we all know that these environments are known and mapped environments. And the ways that these robots operate is that they use methods that have really long and reactive planning times, and they mostly operate in predefined motions or paths. And these environments are designed for robots, and this is why these robots operate really well in these environments. But if we all think about that we all grew up with this promise of helpful robots at home, think about Rosie the Jetson, which was already in 1962. It can clean the house by itself, use conventional cleaning tools like feather duster, and operate other household appliances. And sometimes when it's at home, it also functions as your security system or your babysitter. And as you can see, in everyday environments are more complex than our factory floors. Homes are busy, objects move, people are essentially a part of this loop. And believe it or not, even today, people are trying to replicate Rosie. So this, if you look at this video, this is a very interesting guy called Ziggy who makes these replicas of robots from the early 1900s. And let me outline now in this talk, what does it really take to close this gap to get to real world Rosie that we can have in our homes? So what we want is robots to be assisting us in unstructured environment by combining mobility and manipulation. And we want robots to have flexible task solving and essentially deal with really, really large workspaces that span, for example, our entire apartment or even across many apartments. And by doing this, we want impact in hospitality, logistics, retail, agriculture, and so on. So we notice the common thread here is generality over long horizons rather than a single narrow skill. And we all know that we as humans can perform a diverse set of skills with infinitely many variations of these skills. So in this talk now, I'll focus on three challenges that compound. Those are unknown spaces, reactive interactions, and persistent autonomy. And I'll talk about how our lab is addressing each of these challenges and how they eventually come together in the end. All right, so in the open world, robots rarely have all the information that they need to complete a task since the beginning. So they need to perceive while acting in the environment as well as maintaining a hypothesis of objects and rooms that they encounter. And we know that human-centered spaces require reasoning under partial observability. So in order to tackle this efficiently, we need to learn representations that generalize things like latent concepts and causal relations that end up being and tend to be matter. And robots might acquire new skills, improve their performance over time, as well as generalize to new tasks that you want them to perform. And this requires introspective learning as well as cross-task transfer of these skills. So data collected for one task should nudge the other task to improve the performance. So this essentially means learning on-device signals that tell the robot when it is off distribution and how to recover from them. So another factor is that these spaces that we want robots to operate in can also scale at the size of an entire apartment. So these have many rooms, objects, different ways that you can interact with these objects. And we also often have out of distribution events that are the norm, and these out of distribution events no longer are an exception. So we need policies that plan over these extremely long horizons while still staying grounded in perception. So in this talk, let's take a look at how we can address some of these challenges. So let's start with perception. I'm not going to talk about too much of this in this talk. So we all know that today foundation models have enabled us to significantly advance perception. And to give you a brief overview of some of the work in this direction that we have done recently, I'll briefly talk about this. So first, we are able to learn high quality semantics as little as 10 annotated images, and we're able to achieve comparable performance to fully supervised learning methods that require about 3,000 to 8,000 images. And there's two ways to achieve this. The first is using these foundation models in not training them, but having them frozen, and then either doing pseudo labeling on top or using adapters on top of these foundation models. So adapters are essentially these small encoders that you add in parallel to a frozen foundation model to fine tune to a specific task. And we're also able to segment out of distribution objects. So in addition to a fixed set of semantic classes. So we all know that this is often called as open set perception. And if you want to tackle this, we can leverage, for example, the estimated uncertainty or things like the co-occurrence between different modalities to simultaneously predict now the known classes that you care about, as well as novel unknown objects that end up appearing in the world. And finally, we can build actionable representations such as 3D scene graphs that gives us a nice semantic hierarchy of the scene. And we all know that this is really extremely useful for things such as task planning or reasoning. And I will also talk about this towards the end of this talk. All right, so human environments, especially home environments, contain many articulated objects. And these can be things like cabinets, doors, kitchen drawers, and so on. And estimating the articulation of these objects is essential for robots in order to interact with them autonomously. So in some of our previous work, we have shown that manipulating these articulated objects reliably is feasible if the parameters of the articulations are known beforehand. And we've also done some work before on modeling these articulated objects and their parameters directly from data itself. However, most of these existing works typically operate on isolated object instances, and they assume that you have a very good observability of these articulated objects. We all know that in unstructured home environments, this is typically not always the case. So what we want here is we want robots to learn the articulation reasoning from its surroundings from causal observations of humans. So, or this can also be things like easy to collect demonstration videos or observations in the wild, if you can call this. So we recently proposed an approach that we call as ArtiPoint to address this. So here we propose an entirely training-free approach for detecting articulated object interactions from human demonstrators. So to briefly describe this now, so approach has 4 stages. So Artipoint first uses RGBD observations and optionally camera odometry as input, and it exploits an interaction priors. Now this assumes that any meaningful interaction that can occur in the environment is performed by hands using a human. And we use first any point tracking to first extract the motion of the interaction and then estimate the articulation parameters as well as the location in the 3D space given the camera odometry. So to evaluate this approach in the wild, we introduced a new data set that we call as RT4D. And this data set contains 45 egocentric RGBD sequences across 4 distinct scenes. And this features about 411 human object interactions in the wild. And this gives us scale and diversity that typically single object interactions lack. Now, our results demonstrate that artipoints predict robust point trajectories and reliable articulation estimates on really large scale scenes like the entire room that you see here. Overall, we see reliable inference of the articulation axis as well as its location. Now, perception and articulation essentially sets the stage. So we still need policies to carry over intent of how to interact with these articulated objects. So let's look at how we can achieve that. So we know that teaching robots new skills quickly is convenient. It's conveniently crucial for the broader adoption of robots. So recently we proposed a work that we call as Ditto, and here we address the problem of one-shot imitation learning from human demonstrations, given a single RGBD video recording of a human performing this task. So what we do here is that given this video, for each frame, we extract first the segmentation masks for the hand itself, as well as the object that the hand is holding. And here, for example, in this, you can see that the Coke can, as well as the potential goal object the human is approaching or interacting with. So here, for example, it's the tray that you want to essentially place this Coke can on. So given this set of object masks, we first perform relative pose estimation. We do this to estimate the relative pose of the established object as well as the correspondence between them. Similarly, we also do this in the trajectory extraction step. Finally, we perform trajectory warping. So we blend both these trajectories to retrieve the final trajectory and the start and the object ends the goal that you want to warp this to. Now, lastly, for execution, we just use an off-the-shelf grasping method. In this work, we use contact GraspNet to infer the grasp of the object and execute finally the live trajectory using anything that you want to use, for example, even classical motion planning. So in this work, we show that Ditto first can be successfully applied to a wide variety of tasks, such as placing a sponge on the tray on the top row that you can see here, or a Coke can on the tray on the bottom row. And we show that we can even perform these tasks if the goal location is changed. So it's not exactly in the same place as you saw it in the demonstration. And this is up to a certain level. And using this approach, we're able to teach robots tasks using only one video as a reference. And recently, we all also know that diffusion policies have emerged as really a powerful tool for learning object manipulation. However, they also inherit essentially the core limitations of imitation learning and are restricted to really narrow scope of the expert demonstrations that you might collect or have. On the other hand, we have online reinforcement learning, which can fine-tune these policies, but online reinforcement learning is extremely inefficient. So these need millions of environmental interactions, which really makes it impractical for any real-world robotics. So instead, what we do is we take inspiration from humans, and in humans, dreaming is associated with this enhanced ability to solve next day problems. And this ability to sleep on a problem and wake up with clarity inspires one of our latest works that we call as DIVA. And DIVA stands for Diffusion Policy Adaptation with World Models. And this was recently presented at Coral about a month back. So what we do in DIVA is that we fine-tune diffusion policies entirely offline in a learned world model without any actual real world interaction. So by generating imagined rollouts in the latent space, the robot essentially practices in a dream and it improves skills more efficiently without any physical trials that is needed during fine tuning. So let's briefly look at how this works. So the training process of DIVA consists of 4 stages. So in the first stage, we train a world model on unstructured play data. And this model first captures the environmental dynamics in this really compact latent space that we learn. Next, we encode expert demonstrations into the latents and pre-train a latent condition diffusion policy that denoises the actions. And we know that diffusion offers really diverse guided proposals during the imagination, and this is critical for exploring fixes safely that might not be as safe if you might want to really learn this in the real world. And then the real world, the world model lacks task rewards. So in phase 3, we train a binary classifier on these expert latents to just predict the success or provides rewards during these imagined rollouts. So this helps us avoid any hand engineering for dense signals that we may have. Finally, in the final phase, we fine-tune these diffusion policies using policy gradients on imagined rollouts and entirely in a dream diffusion Markov decision process. So the result that we get is meaningful skill adaptation without any new real-world trials during fine-tuning. Now, to evaluate this approach, on real robots, we collect 4 hours of teleoperated play data using our Franca arm that you can see here. Here we can see the policy improvement across 8 skills on the Kelvin environment. And yeah, so now you see it. To achieve a similar performance with essentially a state-of-the-art online diffusion policy fine-tuning baseline, here we use DPPO. This requires 2.5 million environmental interactions. And we can do this with DIVA entirely in the world model without any real-world interactions. So here we can see now the first skill of opening the drawer. We see that the pre-trained diffusion policy first often struggles to complete the task. So now we see next we see the imagined rollouts now within the latent space where the robot adapts its behavior online. And now finally, we see the fine-tuned policy, which successfully opens the drawer without any real-world interactions during fine-tuning. So with this, we show that DIVA is able to improve robot skills without interacting with the real world. And I think this really demonstrates the capability of DIVA that combines diffusion policies, policy gradients, and learned world model to adapt skills safely, efficiently, and entirely offline.
Abhinav, can I ask a quick question?
Yeah.
Like on the bottom left for the table, it says total physical interactions is 0. So like there was no physical data at all used to
For
train.
fine-tuning, not for fine-tuning the diffusion policy. So it's not trained on data, any environment interaction data from the specific environment. So it is trained on the play data. So that's like just a generic Kelvin play environment.
Okay, well, how do you include the play data into DPPO to make use of it?
What do you mean?
Well, I'm just wondering how you make, like if you're using the play data to help train the diffusion model, are you using any of that data for DPPO here?
No, so DPPO is just trained on directly the environment data. Because I mean, you need to train diffusion policies on the environment data, right? Like the transfer from play data doesn't really happen here.
Okay, did you try anything like that for DPPO?
Not yet, but we're looking into that currently. So we found that we try to train first DPPO on the play data, but it doesn't really work that well if you transfer it because the environments are completely different.
Mhm. Okay. All right. Thank you.
Mhm. Okay, so let's now go back to the kitchen example that we were looking at. Now, imagine a task goal such as, for example, placing a cup on a tray that we saw before. So we all know that language has emerged as a perfect medium for task specifications because this is really an intuitive way for humans to give instructions for robots. And this is why like language condition policies as basically exploded. And the problem is, though, what happens if the provided task description ends up being ambiguous? For example, in this image that you see here, it's not really clear what cup should be placed on the tray as there are many cups. So in order to address this, we recently tackled this with an approach that we call as ambiguous. And here our method aims to solve ambiguities in task descriptions via natural language. So I'll briefly go over how this works. So our solution contains three steps. So first we have task object grounding and ambiguity classification. Here, the model learns to reason about the provided task description and outputs a list of task relevant objects that are requested by the user. And second, the model needs to reason about the observed image to first determine which of the task descriptions are ambiguous or not. Finally, the output that we get from this step is a Boolean value, either to encourage the model to provide justified classification outputs, and we also require an output explanation for this decision. And then in the bottom, if you see in the user query step, if the task description is deemed as ambiguous, then the model must now query the human to ask for clarification. So that's what we do. And this query must be in natural language so that it can be easily understood by users. In this case, the task description in this example is considered as ambiguous. So unambiguous, so a clarifying question is not required. Now, if we have ambiguous, so once the human provides a response to this query that we ask, then the model has to interpret it and ground it in the observed scene. And the output of this step is again a list of task relevant objects. And this time we use it to update include the additional information that we receive. So once all the task relevant objects are uniquely identified, then the model detects the precise coordinate location of these objects in the image. And instead of having to rely on any external object detector, as most prior works do, we can directly output this information using a VLM. So here we use Molmo VLM to do this. And then we see here that in the imagined rollout, play this video here. We can see some of these rollouts where our approach, AmbiRes, is able to disambiguate task descriptions. And then our policy learning approach that we call as TAPAS that was presented previously subsequently now executes this task. All right, so now if we truly want to enable robots to perform a wide range of tasks without being really fixed in their confined workspaces, we need to tackle this challenge of mobile manipulation. And this is important for both service as well as industrial robots. And separating this task into pure navigation to a goal followed by static manipulation is one extremely slow. And for many tasks, such as, for example, door opening, this might not really be possible at all. And whole body motions are extremely hard to define in such cases. So to address this, we proposed an approach that we call as neural navigation for mobile manipulation. And here we decompose the mobile manipulation problem into two. So first we use any arbitrary end effector planner for the end effector. Here this is shown in green. And this end effector planner first generates motions for the end effector in the task space. And then we introduce now a reinforcement learning agent that controls the base. So here, a simple inverse kinematic feasibility becomes a dense reward signal. So the training is both stable as well as task agnostic. And we show that this generalizes to many different types of robots, as well as unseen tasks and environments. Okay, so at one time, so we first trained this in simulation across procedurally generated environments with many different types of robots. So on the left, you see the PR2 robot. We also see the Tiago robot on the right, as well as the HSR robot in the bottom in these procedurally generated environments. And at one time, what we do is that the agent outputs the base velocity, the torso lift if the robot has a torso, as well as the end effector velocities, because we don't want the base to move faster than what the manipulator actions are being performed. And we used robust model-free RL and build an obstacle map from whatever sensors are available. So in this work, we mostly use 2D LiDARs to do this. And crucially here, navigation is conditioned on manipulation intent, and they're not really separate stages. At test time, we evaluate the zero-shot generalization capabilities of our agent. So we construct here unseen tasks from both the linear dynamical system that we use for training, as well as motions based on human demonstrations. So as you can see here in this video, the PR2 here is able to solve tasks that are entirely unseen. So we see pick and place tasks here, but we also have things like door opening and drawer opening. On the right, you see many different types of robots in our lab performing a wide range of tasks such as door opening, drawer opening, pick and place. Also 3 different robots, so PR2, HSR, and Tiago. And here we show that the policies transfer without any retuning. So they're also able to surprisingly handle dynamic obstacles that you see that Tim on the top video is trying to disturb the environment. And this works quite well. Now we use this as a base to do a lot of complex mobile manipulation tasks. So first we enable teleoperation for mobile manipulation. So we use the approach that I just presented now, but we want to collect teleoperation data for a mobile manipulator. And if you can imagine collecting teleoperation data for a mobile manipulator, it's extremely complex because not only that you have to move the arm of the robot for collecting the demonstrations, but you also have to place the base in appropriate location. So with our approach here, the goal is to infer the operator intent for the end effector. So you can manually teleoperate the end effector using your favorite teleoperation interface. And you can leave the base motions to our neural navigation agent that I just presented. So this enables whole body teleoperation for mobile manipulation without any external hardware setup or any additional cost that you may have. So first, what we do is that you see Daniel is just moving the end effector to collect demonstrations here. And we see that the base automatically moves to position itself to ensure that the motions are feasible. And we can see that the operator here is not bound to a tracked workspace. The operator can really move around freely in the environment over really large spatial spaces. And we demonstrate here that our approach results in significant reduction in task completion time across various different robots and environments. So if I fast forward this a bit, here we compare it with different types of teleoperation. So we have our MoMA teleoperation on the type, joystick, as well as VR tracking. And we show that our approach is the fastest to collect this teleoperation data. And now we also use this to actually train an imitation learning policy. And that's what happens here. And we really compare this with whole body motions. And we show that compared to whole body motions that you may have, our end effector with our reinforcement learning agent is faster and also doesn't end up in these kinematically infeasible lock states that you might get with whole body motions. And we do this for different robots for, again, a wide variety of tasks that we collect from the demonstration data using our MoMA teleop approach. All right, so we further extended this. Now we want robots.
Abhinav,
Yeah,
do you mind if I ask another quick question?
yeah, sure, go ahead.
You're not so quick this time, because you had an earlier work where you were showing the like being able to do zero shot manipulation from human, like just videos of humans manipulating objects. So like, how do you compare and contrast the last work? Like, which one do you think is going to be the one that you'd probably spend more time on in order to find and develop policies for one of the issues?
I guess you mean ditto, right? The single shot demonstration work versus the teleop work.
Yes, because
Yeah.
you're also making like teleop much easier in the last one. So then which one do you think is the way to go?
Yeah, great question. So I personally think that we need both. We need to exploit all forms of data. I think teleoperation data is like extremely cumbersome to collect. We all know that. We can only collect as much as data as the number of hours that we can, have the physical robot in the world. And video data, we can exploit like large scale data, unstructured data from the internet, so YouTube or whatever. So I think to make the most of it, we need to combine really structured data that we can collect with teleoperation with essentially unstructured data that we can get on the web. So I think in this talk, I don't have a work that combines both of these, but there are some approaches. Lots of people are working on code training using both video data as well as teleop data. But if you compare these two right now, I would say that the one-shot video only works to a certain extent as long as the goal and the object do not differ significantly. So it really fails if you, for example, I don't know, if you want to move a coffee cup into another place, but you've only held Coke cans. So that's not going to really transfer. Or if you, for example, if you only have the demonstration as placing the cup on the shelf, but now you want to place the cup, I don't know, on the sink or something. So that the transfer across drastic goalposts doesn't really work. But with the teleop approach, this really transfers much better.
Like it transfers in the teleop approach because the teleop has data of other objects, or you can specify the object description differently in the input?
Yeah, exactly.
Okay.
But I think, I mean, if we think about the ultimate thing, I would still think that a combination of simulation, teleop, and video would be the highest that you could do currently to generalize. But then this again brings I think, a lot of problems, like how do we combine this diverse data without really losing the knowledge from each of these that you have? And I think that's a very exciting open problem.
Yeah. Okay. Yeah. Thank you. We'll chat some more at the end if there's time. Go ahead.
All right, so now what I want to talk about is using these whole body motions that we can now do, but also include language instructions for high-level reasoning to perform really long horizon tasks. We all know that LLMs have demonstrated their capability for high-level reasoning, and this is primarily mostly done in tabletop setups for manipulation or in fully observable environments. But mobile manipulation tasks pose a new set of challenges in contrast to tabletop environments, where the camera often captures the entire scene or the full environment. But homes, we know, are partially observable. And to address this, we propose MoMA LLM. So our approach here grounds natural language models within structured representations derived from open vocabulary scene graphs, which are also dynamically updated as the environment is explored. So let's look at how this works. So in our MoMA LLM approach, we first use post RGBD images and semantics as input. and we construct a semantic 3D map from which we extract occupancy maps in the bird's eye view space, and we construct a navigational Voronoi graph. So with this, we also cluster rooms and assign objects to form hierarchical 3D scene graphs. And this gives the LLM a concise and actionable world state that it can use for reasoning. So we then distill the task-relevant knowledge that we obtain from the scene graph into a structured language representation. So this keeps the prompts that you might do grounded in the real-world scene, and we show that it helps minimize hallucinations that we all know that often happens with LLMs. So then the LLM proposes high-level commands which are executed by low-level policies. So the low-level policies can be anything. So this can be your favorite VLA or even classical approaches. So essentially here, the planning and the world state co-evolve as the robot acts in the environment. And this is how we keep the long horizon context consistent. So given object detections, we show that our MoMA LLM approach is zero shot, open vocabulary, and it extends naturally to a spectrum of household tasks. So let's go for an example here. We have a completely unexplored environment, and we give a very high-level instruction like, I'm hungry, find me something to eat for breakfast. So what happens now is that the robot first turns around, sees what objects are nearby, and builds the scene graph, right? So this is what you see here. So, and we also do room classification. So now the robot knows from the objects that's around that it's in a living room. And the task is to find something for breakfast. So then the large language model does the reasoning that if you want to find something for breakfast, we need to typically locate a kitchen or a pantry where food is often stored. And the reasoning here is that there seems to be a door in the living room, which could potentially lead to a kitchen or another area where food could be stored. So here, the action is that go and open the living room door to see what environment is behind the door. So that's what the HSR is doing here. And then it sees a new environment, and again, it tries to classify the objects in this environment and identify what room it is in. So here it sees that it's in the kitchen, and it also noticed that there is a box of cereals on the counter. So then it, in fact, reasons that cereals are typically a breakfast food, and it can be eaten with milk, but there's no milk. And then the reasoning next is go and open the fridge that you see there because maybe there's milk in the fridge. And this all happens directly from the reasoning with the LLM. So now we see that the HSI here is trying to open the fridge door. Then it finds the milk, and this is a successful task execution. So recently, we further extended this to extremely large environments spanning multiple buildings. So for this, the robot has to execute tasks that go from one floor of one building all the way outside and then go to another building. And as you can imagine, the scene graph in this space is extremely, extremely large. And the challenges that we addressed here is how do we use such a large scene representation to reason, because there is a limit of how much data you can input to an LLM nowadays. So here in this recent work that we proposed, that we call as MORE, that was presented at IROS a couple of weeks back, here again, we leverage scene graph to represent the environment, but we differentiate instances and activity filtering task-relevant subgraphs of object and room instances. So this bounds the planning problem and mitigates any hallucination, and it also improves reliability both indoors and outdoors. So here we show that this MORE approach is the first to tackle about 81 diverse tasks on the behavior 1K benchmark, where it's the first approach to successfully solve a significant share of the benchmark tasks. And this essentially, I guess, shows that we can couple perception, articulation, reasoning, and policy learning, all grounded essentially in language to make intuitive interactions. So that brings us to the end of my talk. I'm happy to answer questions you may have.
From the crowd present.
I mean, I can start off with one too. I guess most of the, maybe all the experiments you just showed used a parallel gripper for part of the manipulation. Do you think there's any other mobile manipulation? It's kind of assumed it's kind of like wheels on an arm, and not much detail. So is there anything else related to hardware you're looking into lately, or that might overcome some of the challenges in teleoperation? Because even looking at that last, like the second last example, where you had like the agent embedded teleoperation where people could hold the hand and it would go places. I don't know if there was a button somewhere that made the parallel gripper close, but like also how to do this type of stuff when you get to have more complex hands for robots, which seem to be really popular this year. What are your thoughts?
Yeah, that's a great. So we did have a button to close the gripper in our teleoperation stuff. So we have been working with we've been trying to play around with hands. So it's currently it seems that hands are extremely complex. So I think this is partially about hands, but also how much we have progressed perception and policy learning for parallel grippers, right? This has been like years of work that we have done, and hands have really recently become more popular. So I think there's a lot of gap there of how well we can execute tasks with just a parallel gripper, and how well we can execute tasks with a hand. That being said, it depends on the task that you want to really solve. So I don't think we really need hands for, just pick and place or opening doors or drawers. So it really, if you want to do highly dexterous tasks like, pegging a hole task, or manufacturing tasks like assembling a PCB or something like that. So I think their hands have proven to be really outperforming any normal parallel gripper. Um, but just, normal pick and place, or just articulated object handling, we've still not, I think, found a way to outperform really parallel gripper. And I guess the other question that you also asked, if there are ways, I mean, for automatically I guess grasping objects. So I think this we can already do, right? So we do have quite well pose estimation and affordance estimation and methods that can automatically, find stable grasp poses and close the gripper. So you could theoretically right now couple what we had with just another perception part that does this grasping with it. But again, this is going to be decoupled with the teleop data that you collect, right? So if you really want to have the entire imitation from a human, then we still need ways that the human needs to close it. So one way that I've seen that works really well is with these gloves. I don't know if you have seen them. So, for example, the Manus gloves, lots of people already use it. So you can use them directly instead of the kinesthetic teaching by just demonstrating with these gloves how you grasp the objects, right? And this kind of solves this problem to a certain degree, I think, at the moment.
Yeah, it makes sense. Even though, I don't know, like fingers and hands are complicated, but we don't, like you gave the PCP example, or sorry, not exactly the PCP, whatever. Being able to make boards, like people don't do that by hand. Those are usually really complicated machines that do them in many different layers. So it's kind of an interesting choice, even for some of the companies that are looking at, because it's faster. Like humans aren't fast enough to do it as good as the like custom designed machines.
That's true. I mean, but maybe that was not the best example. But if you see, I think other pure like great manipulation people, they have better examples in which they show all the dexterity that humans can do with their hands, right? Like there's like crazy videos if you watch either Matt Mason's talk, for example. I've seen things that doing with your finger, just flipping coins, for example. I mean, it's just to show how much dexterity human hands can have. And for certain tasks, I definitely think that they're helpful. Whether they are real world industrial tasks or actually assistive robot home tasks, I think that's up debatable.
Okay, thank you.
Maybe I can ask a question. So, thank you for this, pointing me to this Moore paper, very interesting. And I think natural extension, we've been thinking along a lot of the same lines. So some of the criticism I usually get along this line of work is like, or how to put it, like, what is your view with respect to like this new trend of like vision language action models? And obviously you're making some choices here about a specific scene representation and a skill library, which I very much believe is the right way, but other people seem to have like a problem with these kind of inductive biases and that you're limiting the potential generalizability of your approach and blah, blah, blah. So I'm just curious to get your take on this.
I also get this question like all the time. So I think the things that we're trying to do are different and different than what VLM, VLA, what things that you can do with them, because I don't think that anybody has shown that a single VLA can do tasks, larger than a single room, right? So that's the maximum people have reached. We can reach right now, and that is with as much as data as any of the large startups have, like as much as Pi0 does or anybody else, and that even then it's as much as big space that you can do a task is a room. And the type of actions that you want to execute are quite large, so that's great, but they don't really reason as much as these long horizon compounding skill tasks that we try to achieve. So I think that if someone has a great way to look into this with VLAs, that would be great. But currently, I still feel that if we want to do really, extremely long horizon tasks, what really works in the next few years that I would say is still injecting these inductive biases. And we can, of course, use VLAs for any of the sub-policies as we like, but it's not going to do the reasoning that we want, I think, at these long horizon scales.
So, thanks. That's, I think, pretty close what I would have answered, but maybe a follow-up question, which is like, what would you have to see from these other models in order to get you to feel like it's time to change your mind? Like, how could you be convinced? Like, this is something I'm thinking about too. Like, how do we know, when will we know that we're on the wrong side of this? You know what I mean?
Yeah. I mean, I wouldn't say necessarily that they are on the wrong side of this, right? Because I think for some applications and tasks, I could see that in the near future, with as much as data, this could be sufficient, but it's not really going to be sufficient for assistive robots. So that's like my take on it. So when would I be convinced? Okay, that's a great question. Maybe if you can get above 90% success rate in a new environment without any setup. But yeah, or somebody showing tasks at multiple apartment scale, right? Like multiple floors or really long horizon stuff. I think that would convince me that, okay, it's time to push this like even harder. But currently I don't see even like a path to take to do this, right? Like I'm looking for this, but I haven't figured out like, yeah, what do we need to change to make this happen? So just data, I truly believe just data is not the solution. Like that's not going to work. Because already, if you look at all there's like tons of startups in the last 6 months that, that just do data for VLA, and the scale that they're collecting data, which is like, I don't know, there was a recent paper which said something like they collect 110 hours a day or something like that with 60 robots. And that's how much they are collecting data. And that's for a tabletop task, right? Like now imagine if you want to do this for an apartment.
You don't think you could fill a lot of that space with data augmentation from some generative models within the next 6 months?
I mean, combining all of them, if we have a nice way to, solve this embodiment mismatch, I think that could be great. That could really be a game changer. Because currently, I think there's some exploratory work that, exploits all of these together, and that has shown promise. But that's why I mentioned earlier, if we find a way to really not have this embodiment mismatch without like a loss in performance, because currently I think if you combine video data with like sim data with teleop data, your performance is like drops significantly. And this is because of this embodiment mismatch, right? So this core training is also extremely exciting and interesting to work on. If you solve this problem, maybe that's the frontier that we have to push.
Other questions?
I think that's good enough. Okay, we'll wrap it up. Thanks, Abhinav. It's great to have you. Great chats and conversations.
Thanks so much.
Thanks for having me.
Okay.
See you.